Here for tonight. If you guys don't know me, I'm Derek Neparello, the president of SEDS, and this is officially our last speaking event of the semester. However, we do have a couple more events, a joint SGT SEDS party this upcoming Saturday, which we'll get more details of shortly. And then also, the biggest event of the semester, in my opinion, is Yuri's Night, so I hope everyone comes out to that, because that's going to be a great time. That's at NECTO on Thursday, starting I think at 9 o'clock. And we'll have a lot of cool space prizes as well, so make sure you dress up to get a chance to win those prizes. So tickets are $5 individually. You can come up to me or any of the council members as well after our talk to buy some of those. And otherwise, let me introduce our speaker for tonight. It's Al Globus from NASA Ames. So Globus is like I said, research in computer science at NASA Ames. And previously in his career, he did a lot of work on nanomachines as well as developing air traffic management software. But in his free time, he's out in California, so what do you do in California? You surf and you play some music. So he was actually a professional musician for a while before he got into the engineering field, which is always a unique trait. Otherwise, Al is the chairman of the National Space Society and one of the forefront experts on space settlement. So with that, I'll turn it over to Al Globus. So thank you, ladies and gentlemen.
Is this getting picked up?
Yeah.
Yeah? Okay. So I'm going to talk about orbital space settlement. And the reason I'm going to talk about orbital space settlement is because I like them. And I don't really know why I like them, but I think it has something to do with the fact that a future with large-scale orbital space settlement is a really good future. It's a really good future for civilization, it's a great future for people, and it's a great future for life itself, because all of those things will get to do what they like to do most, which is live, grow, and reproduce. So, back in the 1970s, Princeton professor Gerard O'Neill worked with a bunch of students and also with Stanford and NASA Ames Research Center on orbital space settlements, which is one of these guys up here. It's up in space. It's about 900 meters from here to here. This is called the Stanford Torus. That's where it was invented. It rotates. So the people on the inside here, when they're standing, it's rotating around like this, and it feels as if they're in a one gravity field, just like it feels here, or at least pretty close. It's not the same, but it's close. This is a giant mirror that reflects light in. And this is shielding, probably somewhere between 5 and 10 tons per meter squared, so that the cosmic rays don't fry you. And the idea was the government was going to give us an enormous pile of money, and we were going to build these things, and maybe 10,000 people would live here, and they would build these to pay back all that money the government gave us. These are space solar power satellites. It's got large arrays, PV arrays. They collect sunlight, they turn it into power. They give it to an antenna, which is about 1 kilometer across, and that antenna sends energy to Earth, and we sell the energy, and the thing gets paid for. And of course, now, just because you built one, you would not stop. There's the reproduce part, you build another one. For scale, this is something more or less on the size of a shuttle orbiter. So, this is how the inside might look, complete with cheesy architecture from what the 1970s thought would be futuristic. You'll notice it's curved because you're living in a curved world. Only it's not like Earth where things curve like this. Instead, it curves up and a lot more since it's a much smaller system. This river could potentially run all the way around, which would be nice for your boat trip. You just keep going and going, and when you get back to home, you stop. Cylinder is another possible shape for this sort of a system. It has to be some sort of rotationally symmetric system because the rotation is what gives you the 1G so that your children grow up with bones and muscles. These are long, skinny cylinders, and there's a reason why that's a bad idea, which we'll go into later. But the idea is it rotates. One rotates like this, and the other one rotates like that, and they're coupled mechanically and back here, which you can't see because it's really hard to do, and they didn't really know how to do it. But that gives you a net angular momentum of 0, which means that you can keep this pointing towards the sun. These are mirrors, again, that are reflecting natural sunlight. These things here are for growing crops, which presumably can somehow be done in 0G, which actually is plausible. And this system on the inside might look like this, which is obviously put together by a bunch of people from the San Francisco area. You see that there are a couple of people. One thing I've noticed about space settlement designs is they hardly ever have people in them, which seems odd, but okay, now all that material you probably don't want to launch from Earth. You all know it costs $1 bazillion to launch stuff from Earth, and you can dump a lot of pollutants into the atmosphere and so forth and so on. So the idea was you would have a lunar base, and you'd have mines pick up regolith, and you'd use a linear accelerator. Jordan O'Neill did research in electromagnetic acceleration. So, I mean, you know, if that's what your lab does, you figure out some way to use it. But it's not a bad idea, but that's why it came up. So the idea is that you put regolith in electromagnetic buckets, and you accelerate it, and stop the bucket at some point, and the payload keeps going out, and there's a catcher at L2, Lagrange point 2, a stable point in the Earth-Moon system, and it collects all those bags and then takes them to the work site, which was at L5. So this was all great, except that it depended on this vehicle. Remember, this was done in the 70s, early 80s, before the shuttle had flown. Now, before the shuttle flew, it was going to fly 50 times a year. It was going to cost $500 a pound. It was going to fail once in every 100,000 flights. And it was going to be a great vehicle because it was a reusable vehicle. Everything except for this external tank was reusable. The orbiter was reusable, the engine's reusable, the solid rocket booster's reusable. And when it got in orbit, you'd open the things, and then you had the thermal rejection, and things would look pretty, and you could do all kinds of stuff, and it would be really great, and it would be cheap, and it would be reliable. But it wasn't good enough. To do the space settlement, in addition to this, you needed a follow-on heavy lift vehicle where you replaced the orbiter with a system for just lifting very large amounts of stuff. And so that was the idea, and then this happened. This is a Challenger. I think it was 86. Somebody could correct me if I'm wrong. Oh, by the way, please ask questions whenever you have them. Okay, don't have to wait for the end. So I remember spending a morning watching this go over a couple hundred times. So obviously that 1 in 100,000 failure rate was not that great. And just in case nobody noticed, this is the Columbia, which on the way up, a piece of foam came off of that external tank. Let's see, back here. Oops, wrong way. This external tank here was cryogenic. It had liquid oxygen and liquid hydrogen, so it had foam on it as insulation. Well, a little bit of the foam fell off and hit the wing of the vehicle, put a hole in it, and that hole, we didn't know there was a hole in it. When the vehicle came down, you got hot gas inside the wing, ripped the wing off, turned the system to this. This is very unfortunate for a lot of reasons, and one of them is this Kalpana Chawla, who was on board, used to be in the office next to mine when I was doing computational fluid dynamics visualization. So I didn't know her real well, but we did a little bit of work together, and it was a real shame to lose her. This accident was caused by some O-rings that got stiff in low temperatures, and we flew the system at a temperature 20 degrees below what had ever been flown before. So what this basically meant is that all those dreams of space settlement were not going to work because of the transportation system. It's the same reason the Viking attempt to colonize North America failed, because they basically tried to resupply, and their transportation system was rowboats. And you could go downwind with sails, and it just wasn't good enough. And it required the development of sailing vessels, ocean-going sailing vessels that could tack upwind in order to get to North America and exterminate the original inhabitants. So, however, it is a new day. This, right now, is a golden time of launcher development. There are more vehicles being developed by more different kinds of entities, and there are more exciting vehicles being developed than any time in my career, except for during the shuttle, right? Which, of course, didn't quite work out as we had hoped. This is a Falcon 9, SpaceX, Elon Musk. It's a very, so far, reliable vehicle. They blew up their first 3 launches, and they haven't blown up one since. They will blow them up eventually. Okay? Rockets go boom. That's what they do. But for now, it's going really well, and the prices are on the web. Huge innovation. Easy to do, but nobody else does it. This is the Cygnus. Oh, this is built in a factory in the United States, which takes almost raw material in. They build almost everything in the factory. That's very interesting. The new manufacturing process. This is Cygnus. which was developed along with the Falcon 9 in part with NASA money in order to take cargo to the International Space Station, which we'll come back to. It took the opposite approach. It uses engines built, not designed, built in the 1960s, and have been sitting in a warehouse ever since. I mean, I find that mind-boggling. This is Blue Origin. It's being put together by Jeff Bezos, who gets all his money from Amazon. A lot of this, and this is derived from Silicon Valley money too, Elon Musk and PayPal. And this is a vehicle that's been around for a while, has a perfect record. The Atlas V flies with Russian engines, by the way, and it is being upgraded to fly people by the Commercial Crew Program, which is going on at NASA right now. But in any case, there is a reason these vehicles, not only do they exist, but if you look at the launch cost, which was supposed to be $500 a pound for the shuttle back in 1980, if you adjust, LEO is low Earth orbit for those who don't know. If you adjust for inflation and converting to units that make sense, that's $3,000 a kilogram. That's what the shuttle was supposed to cost. So that was a projected. The actual cost was over $64,000, well over $64,000 a kilogram, which is calculated simply by taking the entire cost of the program, dividing by the number of flights, divided by the number of kilograms maximum in a flight. That was 25 tons. The reason it's well over is, in dividing, the reason it's well over is, I don't know any flight that actually had 25 tons. But I couldn't get the data, so I couldn't get the exact number. So anyway, so this is the reason that space settlement had to be abandoned in the early 1980s. This is the reason maybe we should go back at it. This is the projected, meaning the Webb cost of the Falcon 9, which is only a little bit above what the shuttle was supposed to do. And the actual cost, meaning there has actually been a flight with an actual amount of kilograms in it, that was actually paid for, runs out to only about twice that. That's not too bad. Okay, it's only a factor of 2. I mean, much better than this, which is over a factor of 20. Furthermore, SpaceX is developing new vehicles, Falcon Heavy, which has 3 cores instead of 1. Let's see. So this vehicle's got, in the first stage, it's got 1 core, which has 9 engines in it. And the idea for the Falcon Heavy is you strap on 2 more of the same thing. And the Webb cost is $2,400 a kilogram, actually under. And if the projected cost has the same sort of increase here, we're not going to be that far from 3,000. Because we don't know, because it hasn't flown yet. And then the Falcon 9R is coming after that, where they're supposed to reuse the first stage. It looks to me as if, taking this is very inexact, so we say. It looks like that'll be about 3/4 of the cost per kilogram of the Falcon 9, so that will put us right in that 3,000 range. So that says maybe we have a transportation system that can support space settlement. And so some years ago, some Indian students and I designed a space settlement. And last year, Brian Versteeg, who's a great space artist, works with DSI and other organizations, did a visualization of it, which in some ways is not terribly accurate, but looks great. So this is Kalpana 1. It is designed to be the smallest reasonable space settlement that you might want to build for the first one, that you would actually want to live in. It's a home for 3,000 people. It's a little smaller than the Stancil Tortoise. The radius here is 250 meters, which means you have to rotate at 2 RPM to get 1 G. Nobody knows if people can tolerate 2 RPM, 3 RPM, or 1 RPM. Everybody just kind of assumes, and that's what we do. We think 2 RPM will be okay, but we really don't know. It's 325 meters from here to here, and that is chosen to make sure that this system wants to rotate like this, and it doesn't want to rotate end over end. So, which means you don't have to have active control to prevent it. Those long skinny cylinders that we saw in the O'Neill colonies, if you let them spin, they will eventually tumble end over end, which is not good. This is actually thermal radiators. This points towards the sun. There's a shade. This is artist stuff. But looking good is important. And so in any case, so you can make these bigger or smaller. It turns out that most of the energy use, because this does not have natural light coming in, most of the energy use is for agriculture, grow lights. And the original design uses halogen, yeah?
This is the lower limit? Is there an upper limit to how big something with this basic could be?
Just strength of materials.
Okay.
And when O'Neill was doing these studies, I haven't done the calculations myself, populations in the millions is possible.
Thank you.
And he didn't have carbon nanotubes. So, okay, you might be able to get a little better than that. So, so in any case, with the advent of LED lighting, it's much more efficient. The original thing had to have a space solar power satellite somewhere to deliver extra energy, microwave energy to this exterior here. It looks like you don't need that. It looks like body-mounted solar cells, making some assumptions about efficiency improvements, because this isn't going to get made tomorrow, right? It's going to be a while. It looks like you might get enough power off body-mounted to run all the LED lights and all the lighting and all the other power that you need, which would simplify the system quite a bit. This is actually supposed to come out more, this end cap, but be lightweight. And the idea is that you'll put some coatings on so the light comes in and then bounces off. And you get diffused sunlight at low levels throughout the whole colony. And we hope it will be a little bit like living in Alaska in the summer. In other words, you get natural lighting 24/7, but you don't get that day thing. So here's some interior views. This is artist rendition. He added that, all this light coming in. I think I know how to pull that off with light pipes, but I don't really know. That's an example of interaction between the artist and the engineer. And you notice this is the place to live. There's a baseball field and there's a golf course. I used to play sports, so we have this sort of thing. A couple other. Here's another one. The thing to notice is this expensive furniture sitting outside. You don't have to worry about rain, okay? The rain, the sprinklers. You put the sprinklers where you want them. You just make sure it doesn't rain here. Problem solved, right? And then there's an additional source of materials. In the 70s, we didn't realize that we were in a cosmic shooting gallery. And it started when the space colony's work went into the 80s. Brian O'Leary suggested that they started discovering these near-Earth objects, NEOs, and so suggested that maybe another source of materials. So here's some images. These are Brian Versteeg's stuff here. This was done for DSI, and the idea is you have these big asteroids. They have lots of materials. You could build your space settlement right next to your materials. That might be a good thing to do. Or you might even be able to pluck materials and bring them to where it is you want them. So it's an alternate source of materials. The moon still might be better, but at least you have two options instead of one. So at this point, hopefully you will think that orbital space settlements look really cool. It might be a fun place to live. But they're going to be expensive. They're going to be extremely expensive. And you might ask why. And the first answer is that someday something really bad is going to happen to Earth and we're all going to die. And so before then, we would like to have space settlements so that not all of humanity and all of civilization is exterminated. This is, of course, an artist's conception of the dinosaurs being exterminated. We don't really know, but calculations suggest that this collision with a 10-kilometer asteroid caught the atmosphere on fire and burned everything above ground to a crisp. Okay? That is an environmental problem. Now, this happened about 66 million years ago. Calculations suggest it should happen about once every 100 million years. So we're kind of due. Not that really means anything statistically. But just in case we forgot that this was important, this is what happened over Russia last year in February. It did some damage on the ground. This was probably maybe 15, 16, 17 meters in diameter, something like that. It came on the sunward side. We couldn't see it coming. And it was definitely, for a lot of people, a wake-up call that maybe we should do something about that. So one of the reasons is survival. This is one possible bad thing to happen to Earth. There are others. Take your favorite. They're in the news all the time. The second one is growth. Living things like to grow. And the way you avoid going extinct is to grow. If all you can do is live in one habitat, you've got some species that lives in one lake in Oregon, then you have to depend on the EPA and local protesters to keep your species alive, because if some developer wants to come in and use that lake for something, you're host. If you grow, if you spread out, if you're like humanity and live on every single continent in the entire world, then you're much more likely to survive. And if you grow off planet, you're even more likely to survive, significantly more likely to survive. And growth with orbital settlement is very significant. Take Ceres, tear it to pieces, turn it into orbital settlements, somewhere between 100 and 1,000 times the surface area of the Earth. That's how much living area you get. 1G living area, doesn't count the other stuff you can get. The species this way, no problem. Exactly how many trillions you can argue about, but trillions, no problem. And furthermore, this is all no land. I mean, what would have happened if when the Germans were resurgent after the First World War in the 30s, Hitler took over, if in order to get their Lebensraum, they could build it. They didn't have to conquer it from Russia and from Poland and from France and so forth and so on. That's a whole, I'm not saying they would have taken that path, but that path was not available to them. What would have happened after the Second World War if the Jews had had an option to not go to some place where everybody around them wanted to kill them, but rather some place where there simply wasn't anybody, and so nobody would want to kill them? These situations are not situations that are never going to happen again. They are going to happen again. And if there is a mechanism for countries and racial groups and whatever for it to grow and grow greatly without taking somebody else's territory, and every single inch of land in this planet today is owned by somebody and has 2 or 3 other people that really would like to have it. This is a way around that dilemma. The last one is wealth and power. And wealth and power is good because who wouldn't want to be wealthy? And who wouldn't want to be powerful? You can use it any way you want. And there's some object lessons in terms of expansionistic versus stay at home. Okay? When you grow and you expand, you gain power and wealth. When you stay at home, you don't. And the classic example is the Ming Dynasty. For a while, they had a fleet of hundreds of large junks, much bigger than anything Europe put together. It traveled around the Indian Ocean and parts of the Pacific. We don't know exactly where it went, but we have an idea. And China was about to become that expansionistic power that Europe became. And there was a struggle in the court. The expansionistic society, the naval people lost. The fleet was recalled. It was burned. My guess is a good number of the officers were put to death. And laws were passed prohibiting the building of ocean-going ships. The plans were destroyed. And just a few years later, the Portuguese showed up in Macau. Okay? So basically the argument was we shouldn't waste our money in all this other lands. We should spend our money at home. Sound familiar? Have you heard this before? Right? And it was a disaster. I mean, a true and massive disaster. Okay? And the wealth and power comes from energy and materials. What can we get if we go to space system? This number is simply the total amount of energy the sun puts out over the total amount of solar energy that impacts the Earth, which of course is multiple orders of magnitude more than the gas and oil and stuff that we burn. So energy resources might as well be infinite for the foreseeable future. And the materials resources are also enormous. This is one near-Earth object, NEO stands for near-Earth object. Those are rocks that cross Earth's orbit or come close to it. There's one particular one in the 90s was calculated what's the total value of the platinum group metals in it. The TR is not that's not a typo. That's the value of the materials. And that's why there are organizations like Planetary Resources and BSI that are interested in asteroid mining, although they are probably premature. And furthermore, Moon is just one asteroid. If you include the belt, there are thousands of objects like this. So wealth and power, growth, and survival. All pointless if it's not a nice place to live. Why would you go there if it's not a nice place to live? The people on these things are going to be living in a gigantic machine. If they are not tech savvy, they're going to be dead. They can get a good job on Earth, So what's good? Okay, first of all, great views. If you talk to any of the astronauts, they'll tell you, what do you really want to do? I want to go to the cupola, and I want to look out, and I want to watch the Earth, okay? Because it's great. And anybody in real estate will tell you, how do you make, if a room with a view is worth more than a room without a view? A lot more. Low-G recreation. This seems trivial, but how many people live in Hawaii so they can surf? And how many people live in Colorado so they can ski? And the answer is a very large number. These are some people enjoying brief moments of zero-G. You get an aircraft, and you fly up like this, and then on the way down, you get this for about 30 seconds. And the way up, you can do that. You can get maybe 4 or 5 or 6 of these things before you start to throw up. And at that point, the commercial guys stop. Did you go on that trip that guy tried to give you?
Yes.
How was it?
3 hours of a roller coaster in the sky. It was, it's like after the first plummet that you start to vomit.
Oh.
It goes into the bark bag.
Yeah. Okay, so the voice of experience. Of course, dancers and gymnasts are going to go nuts. Because if in a space settlement, because they're rotating around axis, so I didn't go over this, it's fairly obvious, but now they got it. At the axis of rotation, you have 0G, you have no force on you. And as you go just a little out, you have a little bit of force. So you can easily strap on wings and flap and fly around. Do what Icarus did, only without the sun thing. And sports, of all the major sports, oh yeah, go ahead.
So, I have a question about artificial gravity.
Uh-huh.
Isn't it dependent on the fact that you are on a surface and
Yes.
the equivalent to your axis of rotation?
Yes, absolutely.
So, things such as, like, there's the example of the artist relation where there's baseball. You hit the baseball, then it's just going to float away.
Well, it's not going to float away. It's going to go on. It's going to go in a straight line from. Let's ignore aerodynamic effects. On the little things. It's going to go in a straight line, and at the same time, just going in a straight line, the vehicle is going to rotate. So it's going to come. It's not just going to float. It's going to go back and it's going to hit some particular place, but it's not going to be the same place as it would have been in Dodger Stadium. And if any of you guys can write fiction, I had this great idea. Well, I think it's great. Give me just a second. I'll get back to you. And the idea is you have, in the space colony, there's like an exceptionally good local team. And so they invite the New York Yankees to a match because they know that, this thing, but then the Yankees, they say, well, you just come on up, we'll play a game. You don't need to practice, don't worry about it. The Yankees get smart. They go, oh no, we know this rotating environment is going to be a problem. So we're going to insist that we get to have batting practice, right, before the game. And so then the colonists, they build two baseball diamonds, one of them facing, if it's rotating like this, one of them facing this, and one of them facing this. And then the game happens, of course, it's all a race between the superior athleticism of the Yankees and their ability to deal with the fact that the ball is not going where it's supposed to go. So, and then of course the ending is a secret, I don't want to spoil it. All right, you had a question.
I'm a professional science fiction author. We should talk after this.
Great,
sell
yes,
that
I'll
idea.
give you the card. So you're exactly right. Pseudogravity is not gravity.
And you still have a lot
Okay.
of problems with it,
Oh, yeah, well, you can have a lot of problems and a lot of opportunity too. It's actually possible, there's a paper from years ago where it's actually possible to have a fountain that does a figure 8. If you're very careful about which way you spray things. And there's issues of will people be able to adapt? My guess is, and people are pretty adaptable. I mean, they can live in igloos and they can live on the equator. My guess is that people figure out these are all things we're going to have to work out. And then the last thing is an independence. On Earth, we are all interdependent. Everything that I dump into the atmosphere, you breathe. So that means you get to have a say in what I do. Now, within this individual space settlement, everybody's extremely dependent because they're a small ecosystem, but between settlements, there's no connection. You have hundreds, if not thousands of miles of vacuum separating you. So if you want to go and pollute your environment and your space settlement, your problem, not mine. I've got my own space settlement. And the borders, how many of you have seen Elysium? The movie, yeah. The borders there, that doesn't work. The borders are extremely easy to control. You have to come through an airlock. In Elysium, for those who weren't there, there's a toroidal colony with no top. Okay, and the reason for that was so that people could sneak in on spaceships, which was very important to the story, and it was a movie, not an engineering design. So here's a little who, what, where, why, when, this stuff that you're supposed to do as journalists. So this is students for the exploration and development of space. I'm pretty sure this is Buzz Aldrin. You can't really tell, but I'm pretty sure that's who it is. This is what you do when you explore. You go to places nobody ever been, and you get out, and you're very square-jawed, and you're heroic, and it's really great and really wonderful. And about 3 weeks later, you move on to something else. If you're not the guy who actually went. Space settlement is about, how many people recognize this family? Yeah, it's TV family. Right. But the key to settlement, the difference between a settlement and a space station is kids. If you raise your kids, it's a space settlement. If you don't, it isn't. It's something else. And just as an aside, which we'll get to. My prediction is the first permanent residents in space will be maids. Possibly repairmen, but most likely maids, and we'll see why in a little bit. So, most of the people, when they think about space settlement, they don't think about orbital space settlement. You go on the moon or Mars, right? Everybody knows that Mars is where you're going to do settlements, right? I think everybody's wrong. And the reason is, the big one to me is, if you raise your kids on the Moon or Mars, they're going to grow up in a 1/6 to 1/3 G. And we don't really know quite what's going to happen to them, but one thing we know for sure is they're going to grow up with weak muscles and they're going to grow up with weak bones. And so if your kid is a great, then you're not going to be able to go to Earth. Okay, if you go to Earth, you might be able to sit in a wheelchair, but more likely you will be flat on your back the whole time. So if you have a kid who's a great musician, they aren't going to play Carnegie Hall. And if they're a great athlete, they are not going to compete in the Olympics. And if they're a great scholar, they're not going to go to the great universities of Earth. They're not going to go to Harvard. They're not going to go to Stanford. They're not going to go to Oxford. They're not going to the University of Michigan. Okay? This is not going to happen. And to me, being a parent, that is completely, totally unacceptable. And I believe that in 20 years, that will be unacceptable to you too. So, and as we've gone before, in a rotating environment, you can get something that feels a lot like 1G. Your kids will grow up with muscles and bones, and they will get to do all those good things. There's also some simpler stuff. You can put your settlements close to Earth, so your logistics are simple. Do not ever underestimate the importance of logistics. It is key to almost everything. And a little bit careful with your orbit. You'll have all the solar energy you want, pretty much 24/7. On the Moon and Mars, of course, you have nighttime. And on Mars, you have dust storms. So you have to depend, usually have to have a nuclear energy source. The other thing is growth. I mean, if you put the total land area of the Moon and Mars together, it roughly doubles the land area of Earth. This is great, nothing wrong with doubling. But of course, as we've seen, with orbital settlements, you get factors that are much higher. And last is, it's possible to service some Earth markets on the Moon. Mars, there's no way, this is too far away. With orbital space settlements, you can service markets, and so you can have some sort of commercial viability, or at least we hope it can. There is one absolutely enormous disadvantage, which I'm sure you've already thought of, is in orbit there aren't any materials. You get a couple of atoms per square cubic centimeter, that's it. The elegant solution we have already seen. Build your settlement next to an asteroid. There are asteroids much easier to get to than Mars. Some of them are easier to get to the Moon. They do have a tendency to go far away from the Earth. But there's actually even a solution to that. This is a mission that NASA is working on to grab an asteroid, bring it into Earth orbit. Actually lunar orbit. If you do that a lot, and by a lot I mean approximately 14,000 times, you can get enough materials to build Kalpana 1, assuming that most of your materials are driven by your shielding requirements. There are asteroids big enough to build Kalpana 1, give or take, about 20,000 that are in your orbit. That's a lot. And many of those you can build many Kalpana 1s or a very much larger system. So this is an elegant solution to the materials problem. It's still more difficult than getting a bulldozer and piling up regolith, but it's much easier than getting it out of nothing. So that's all theory. That's all, thinking and stuff like that. There's not data that says that it's easier to build things in Earth orbit or orbit in general than on the Moon and Mars. But there's empirical evidence. We've been doing this is the International Space Station. We've been doing this since the 70s. Okay? And the Russians have done it, and we've done it together, and the Chinese are working up to doing it. This has been done. If we're really lucky, maybe we'll build a lunar base in the 2020s. Maybe. There's no firm plans to do it. There's no funding to do it. But maybe. And Mars is much harder, so who knows? So empirically, we know that making space settlements is much easier, space stations is much easier in orbit than on the Moon and Mars, but that's the way it is. So, let's assume for the moment that I've convinced you that building space settlements is a really great idea. There's a minor problem is how. Which, of course, is an enormous set of engineering problems, which is great, because we're engineers, right? And what do you want more than interesting problems? However, there are some problems. The government is not going to give us enough money to do this. It isn't going to happen. It's a lot of money. And the technology and infrastructure are not ready to do this in anything resembling an inexpensive way. So the basic idea is to do things that make sense in and of themselves, and use those to build, to develop the technology and the capabilities that we need for space settlement. And having spent a lot of time looking for these, and if anybody can add one, I would love it. These things are space tourism, space solar power, and planetary defense. Okay. So we're getting to know what we need to understand why those things give us those things, the things that we want. The most important one is better Earth to orbit transportation. We have to build really big things in orbit, considerably bigger than we've built before. We need to protect ourselves from radiation. We need to recycle our air, water, food, and waste. We need to pay for it. Okay? So, oops. There's the launch problem. Failure rate about 1%, thousands of dollars per kilogram. You know, it's all sorts of optimizations and stuff you have that forces on the spacecraft, makes them more expensive. But the root cause of all this is low volume. We launch maybe 100 times a year, 60, 70 times a year, 80 times a year. If we only drove cars 100 times a year worldwide, I can assure you that those trips would be god-awful expensive. We need to increase the volume. We need to increase it a lot. Now, this number is mostly pulled out of the hat, but something on the order of 10,000. If you can't do 10,000 launches a year, you probably can't get the price down to something that will allow you to build something as big as a space settlement. That's a guess. Maybe it's 5,000, maybe it's 15,000, I don't know, but it's something on that order. Tourism can get you there. Okay? The current applications, you know, Earth observation, communication, and so forth, you don't need 10,000 launches, not even close. Tourism can get you there. So this is, people were asked the question, if you had to pay this much money for a vacation in space, how many would go? And then from that, they calculated the number of people that would yearly. So at $500,000, you get 170 people a year. You know, they fly 10 at a time. That's 17 launches. That does nothing. This doesn't help much more. But if we can get in this range, according to this study, right, all of a sudden, demand explodes. That's, if you're flying 10 people at a time, 40,000 launches. That's what we need to get. Now, this number isn't right, of course. Maybe it should be 50,000, maybe it should be 150,000. But there is a number somewhere around here that tourism takes off, and we get our 10,000 launches a year. Tourism is nice because it's got this nice smooth path. Suborbital, you go straight up, straight down. Orbital, you go up, you go around and around and around. Orbital hotels, you go up, you drop people off at a hotel, you go back. A low-G retirement homes will go into. Basically, you live up there if you're old and decrepit. I'm getting there. You got a while to wait. Then, once you've done that, if you rotate it up, you can get a space colony. But it'll be expensive at first. But there are some groups of people on this planet with enormous amounts of money and a desire to not live with everybody else. And we hope they'll pay a premium to do that. And then from there, we can get to general space shuttle, get the price down. So, suborbital tourism. The great news is you can buy a ticket today. The bad news is you can't actually fly. So, there are two companies doing this. Virgin Galactic, who wants $250,000 for your flight. They claim to have 600 customers and $80 million in deposits. They're very serious about this. And there's a demo. This is their vehicle. This guy goes into space. This is an airplane that takes you up to 50,000 feet and you blast off. This is called Spaceship 2. It is the demo for Spaceship 2 was Spaceship 1, which flew into space twice in 2004 to win the $10 million Ansari Prize. And then there's another, that's this vehicle won that. This vehicle, X-Corp, was in that race but didn't quite win. They're a little cheaper because when you go up in their vehicle, this is Photoshop. This is real. Okay. So when you go up in the X-Corp vehicle, you're strapped in. If you go up in the Virgin Galactic vehicle, assuming all this happens, you get 5 minutes of free fall where you get to unstrap and play around. So that's what you get for $155,000. Here's the bad news. Remember, this demo was done in 2004. It's been 10 years, and we do not have operational flights. There are 3 dead engineers when a rocket blew up. There used to be this meme, which isn't so common in the space world, that the reason that all these great things weren't happening is because the government was a bunch of stupid imbeciles, and NASA couldn't do anything, and they were getting in the way, and blah, 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 blah. Okay, suborbital is the easiest thing to do. And it has taken 10 years. And we have not got from the demo to operational. The reason that we don't have what we want in space is not because the government is a bunch of idiots and NASA can't do anything. It's because it's really hard to do. And the private industry is having as much or more trouble than NASA ever had. So, next to orbital. That's the next thing, right? And the good news is the President of the United States is doing his best to try to give us this program. Because what you need for orbital tourism is you need a vehicle that can take people up into space that is a private vehicle, because the US government cannot fly rich tourists into space politically. It doesn't work. But if you have these private guys, then they can fly them up into space. So the idea was they paid a bunch of guys, Orbital and SpaceX, to develop rockets that then take cargo to the International Space Station. The Obama administration says, that was a great idea. Let's do the same thing for people. And that is working its way through Congress. Congress likes to not fund it all the way, but funding has been ramping up by about $200 million a year. The whole idea is to not have to fly with the Russians at $71 million a seat, and you lose Crimea in the process. So there's a couple of companies working on this. It's a very promising program, and I hope it succeeds. And if it succeeds, you could potentially have orbital tourism, but you can even do better. Because the obvious thing is you don't use your vehicle. You can drop people off at the hotel. That's the right way to do it. And just to make sure that things were true, this has already been done. The Russians have been flying space tourists for 10 years or so. Can't remember exactly when. This is Dennis Tito, the first guy that flew. He paid, I think, about $20 million to the Russians. There was an extra seat on the Soyuz. The Russians didn't have to pay the cost of they already the sunk cost in building the space station and all the technology development. So they needed some money, so they got $20 million to fly this guy, and he's having a great time. Then there's been 6 or 7 other tourists. This is Ansari, as in Ansari X Prize. She also flew. And the current price, I believe, is supposed to be about $40 million, and there's actually an opera star that is going to fly. So, of course, you can't have a business based on taking advantage of a $100 billion government project in order to fly $20 million tourists. That has a very limited number of people that can do that. So there's a guy, Bigelow, who doesn't think he's in the space hotel business, and he may be right, I'm not sure, but he's actually a Las Vegas hotel guy. That's where he made his money. And he got some inflatable technology from NASA, made it better, flew a couple of sub-sized vehicles. This is Earth, and this is a vehicle actually in space. It has a pressurized volume, it has air in it. You could breathe in it for a little while because there's no regeneration of the oxygen, so you can only do it for a little while, and then you'd be dead. His target market is actually national space programs. This is a relatively cheap thing to do, so maybe Brazil or Australia or India or Saudi Arabia or something could have their own national space program by renting out these modules. This is some of the modules you see that people for scale right here that they're working on. These will have life support systems. He is going to launch supposedly in a few years. He's going to fly a module in the International Space Station, which will be very helpful for finding problems. And then, just like SpaceX, they put the cost on the web, okay? That's the cost to fly for one seat on a SpaceX vehicle to go to Bigelow Station. Of course, the station's not up there yet, so there's a little bit of speculation. And you can fly up to 7 people at a time. And you have to pay Bigelow $25 million for 1/3 of one module for 60 days, which works out to $150 million for both modules. And this, remember I said, I was a little bit of a jock in high school, not a particularly successful one, but I had a good time. I think we can do space. I need an entrepreneur who's really good at this sort of stuff to put on the first Space Olympics. Because if you work this out for the whole module and you want to fly 6 famous athletes and a cameraman, that will cost you about $350 million. So the idea is you go up, you train for 50 days, and then you have 10 days of games. And you're going to get a lot of eyeballs. And sports that get a lot of eyeballs can make a lot of money. Here's the sort of kind of money that's brought in by big sporting events. And notice the ones that go on for a while, like the Olympics goes on for a couple of weeks, World Cup goes on for about a month or two, they can pull in the kind of money that is necessary to actually make a profit. Of course, you need a video feed, but TDRS, which is a satellite system that NASA runs that's able to track a vehicle in low Earth orbit, this is not going to matter in terms of prices. So listen, we don't have any budding entrepreneurs. Well, let's suppose that Bigelow builds his things, and let's suppose that they are used by tourists, and let's suppose that it all works out and people make money. People make money, they'll build more hotels, there'll be lots of hotels, there'll be lots of cool hotels, and nobody's going to want to fly, spend hundreds of thousands of dollars to fly their family on these things and then eat freeze-dried junk. Okay? You want good food. And if you want good food, you have to grow it. And so this tourism business, the tourism as well as giving us the flight rate we need in order to be able to build space shuttle, is also going to give us life support. They're also going to have to recycle their air and water better than is done now, and they're going to have to learn how to recycle solid waste and food. So, the next step. This is Stephen Hawking's on one of those zero-G flights. Most of you probably know that he's a brilliant physicist. He can move one finger, or at least he used to be able to. This is probably the first time he's been out of a wheelchair in bed in decades. And people are going to notice when they go to these space hotels that they don't need a wheelchair and they don't need a walker. And so when they get old and decrepit and hopefully still rich, they're going to want these sorts of things, right? And the grandkids are going to want to visit because they get to play in the zero-G playground. Okay? This is very important. You cannot have a program like this if the grandkids can't visit. The other thing you have to happen is if you're in a space hotel and somebody gets sick, you stabilize them, you send them down to Earth, you let Earth take care of them. These people that we're talking, the market here is old, decrepit people who are really sick and will get sicker and sicker and sicker. So you need top-rate medical facilities because they're going to have diabetes and Parkinson's and they're going to get heart attacks and cancer and all that sort of stuff. But this is the only difference between a space hotel and a low-G retirement facility. Oh, and also you can't send these guys up. They've been up there for a couple of years, so they're not going to be able to go home anyways. So I'm going to leave it at that. You know, the next two steps are not that particularly interesting, and move on to the other path, second path, space solar power. The idea is you gather energy in space, you convert it to microwaves, and you send it to Earth, where you have an enormous antenna that gets it. This is extraordinarily difficult to do. It is even more difficult to do profitably. And I kind of guess that, I don't know if it can be done profitably, but it's worth trying. Because if you succeed, you can solve the energy and global warming. You know, most of the things people talk about global warming or energy, they say, well, this will take a step in the right direction. Oh, this will be better, right? This won't be a step in the right direction. It won't be better, just solve the bloody problem. If we can make it work, which is a big if. It's very similar to fusion. It's extremely high risk and enormous payoff. But here's the weird thing. Fusion gets about $400 million a year in funding, and has been getting that funding for decades and decades and decades without ever producing a bloody watt of power. Space solar power gets nothing. Like 2 years ago, we got $100,000. Okay, but that was a huge increase, right, over what had been before. And it seems to me much more promising. So, I don't know. And you know, it is an enormous engineering problem. Like I said, from the point of view of most of the people in this room, that's good, not bad. And if you can pull off space solar power, if you can really deliver a substantial fraction of Earth's energy, you solve the launch problem. You get lots of launches. Here's energy use back from 1820 to the present. Okay, it's obviously taking off. It's going to continue to go up because even if people like us conserve and start using half as much energy as we used to, there are a couple of billion people on this planet who don't have electrical power, who don't have internal combustion engines for all practical purposes, and they're going to want those things, and they deserve them just as much as anybody else. The total market's about 10 terawatts. 400 satellites with a 10-kilometer radius should be able, you know, with some reasonable assumptions, should be able to meet that entire market. Now, somebody got really mad at me because they didn't notice that this was radius instead of diameter and told me that I was off by a factor of 4. But it turns out they eventually noticed that it was radius. If you assume, make some assumptions about how much power per kilogram, it's about 18 megatons of satellite. That's 340,000 Falcon launches. That's a lot of launches, okay? And by the time, this is such a big market that even if you complete these launches, you build all these satellites, if they have a 50-year life, you just have to start making new ones anyways because they start running out of lifetime. So you can justify launches for a very long time doing this. And of course, this is an enormously expensive thing to do. But this is the total amount of money that you can make if you sold it. This is about half the market price right now. That's a lot of money, okay? $8 trillion. And this is something that I really think we should pursue. Even if we don't succeed, we will learn lots of interesting things. Okay. So the last of the paths that I've been able to find, and please tell me if you can find any other ones, is planetary defense. Planetary defense, meaning defense from things hitting the planet, not, you know, Russians versus Americans or something. Here's the basic problem. This is the orbit of various planets. There's the sun, and all these other dots are known asteroids. The green ones and the purple ones we don't really care about too much, but the red ones are the ones that cross Earth's orbit and potentially hit us. And when they hit us, they do stuff like this, which is very bad if you happen to be close by. Or this, in Russia, I said, was it 20 million trees or 80 million trees were knocked down by maybe a 30 or 40 or 50 meter diameter asteroid, and hers are, last year's Russian hit too. So we need to do something about this. This is a core function of government defense, as our friends up in the upper row know. It doesn't make money, but it's really something we ought to do. Here is, for a talk like this, you have to have at least one XY plot that nobody understands. On the bottom here we have, this is log plot. So here's the diameter of an asteroid. Here is the absolute magnitude, which is the amount of light reflected by it in a certain distance and so forth and so on. There's a lot of assumptions in here, but you notice it's the opposite direction, but it's a log scale. That's why it looks linear here. This is the total number of that cross Earth's orbit or nearly cross Earth's orbit. And assuming some certain random properties, this is the interval at which they hit. This is the destruction of the dinosaurs. This is those 20 or 80 million trees, I can't remember which one, that the Russians knocked down. So this happens every 100 years or so, or maybe 50 years or whatever, on average. Doesn't mean it can't happen tomorrow 3 times. Okay? And this is 100 million or so. Again, it's on the average. There's no particular reason it couldn't happen in 15 minutes. It turns out it probably won't, but there's not actually any guarantee. So, what do you need to do about it? The most important thing to do about it for planetary defense is detection. If you don't see it coming, there's nothing we can do about it. If we do see it coming, and we can say, we're going to get hit in 2030, and it's going to hit Rio de Janeiro at 9:15 on Wednesday morning, we'll have all the money we need for deflection. Okay? No problem. That's going to be, anybody can put that in front of Congress, right? So what have we done in terms of detection so far? Well, of the guys that are really going to hurt, the 1 kilogram and bigger, that have globally devastating effects, we know where about 95% of them are. There's about 1,000 total. That's a kilometer big. Of the guys that will do regional destruction, okay, maybe only take out North America, say. Okay, we know where a grand total of 10% of those guys are. There's about 20,000 all total. And of course, as we've seen, these all have enough materials to build at least 1 car per 1. The city killers, there's about 1 million of those. That's 10 meters and greater. We know we're a grand total of 1%. Now the good news is when you get hit by, I'll just a second, when you get hit by a city killer, there's very rarely a city underneath it. Okay? There's a big world and small, and then the cities are kind of small. But it's so. So you had a question?
I want to know what percentage of things we don't know.
These are estimates. These are estimates based on detection. We know the volume we've searched. We know how bright something has to be in order to then search, and you do a whole bunch of calculations by people significantly smarter than I am, and they come up with these numbers. These numbers could change by a lot with new discoveries. We probably do have this one right, because we think we've actually found all of them, and the discovery rate has really fallen off. Right? So we're probably right about this. But the thing is, you never know if there's one more, and it's got your name on it. Right? And it's the same problem with crossing a street where there's very little traffic. You cross the street with very little traffic, do you just walk and don't look? Well, no, there's very little traffic, so it's hardly ever going to get hit, but you still look, right? The reason you look is because the consequences of being wrong are so tremendously high, and it costs you so very little to look, okay? The other thing, this detection cost doesn't cost a lot of money. A couple of planetary missions would pay for it easy. And here's the thing, of all these guys, about 2%, if we don't do anything, about 2% will eventually hit Earth. And that's just calculated from the frequency of collision, the number of them, and the lifetime, which is probably around 10 million years. The funding for this activity, which seems to be extremely important, is pathetic. Okay? It was running about 20 million a year in the last fiscal year. It's a little more now because they're ramping up for some other things. And in the face of government not doing what its job is, others have tried to step into the breach. The B612 Foundation, anybody here watch Scandal? Okay, okay, well it's not B13, 613, it's B612. B612 Foundation have designed and are trying to build a satellite, infrared space telescope that should find about 90% of these guys. And they'll find a lot of these in the same thing. We'll go over that, why that. It's a little nonprofit, you can give them money. They need kind of a lot of money, But it turns out that you can do this sort of thing. You can raise hundreds of millions of dollars for a university building or the wing of a library. So maybe you could be able to raise it in order to save the planet. So here's why the Sentinel should work. This is the orbit of Earth. This is the orbit of Venus. This is a proposed orbit of Sentinel. If you do your search from Earth, which is how we do it now, you can't look towards the sun, so you can only see asteroids, for the most part, that are farther from Earth, are farther from the sun than Earth is. Okay? And then you've got night and clouds and all that sort of stuff. If you put your satellite near the orbit of Venus or anywhere in the interior, not only can you see a bigger chunk of what's going on, but you can see the guys that are inside of Earth's orbit. In addition, you can look in the infrared, which is mostly absorbed by the atmosphere, and that makes it much easier to find asteroids because asteroids have an extremely low albedo in the optical, so that not a whole lot of photons get reflected, but they emit energy in the infrared, so it's much easier to find them. The reason that you want to go for an orbit near Venus is you can use a Venus gravity assist to get you into the orbit, so your total delta V requirements are significantly less. So, if we found somebody, is there anything we can do about it? And the answer is yes, and it turns out it's not even very hard. You know, imagine you're driving down the street and a couple hundred yards in front of you, a pedestrian starts crossing. If you continue at your same speed, you're going to hit him. So what do? You slow down a little bit. They walk across the street and you miss him. Same deal. If we've got an asteroid that's going to hit us, all we have to do is deflect it just a little bit. If we can get it to arrive at Earth's orbit 4 minutes later or sooner, it will miss us. And if you discover it with 10 years to go, which is very plausible, you have to give it 1 millimeter per second delta V. I think we can pull that off, okay? And the other thing is we will probably find it much sooner because we can predict, with ground-based data, we can predict the location of asteroids for about a century. So if we look out, if we really find all the guys out there, most likely we're going to find they're going to hit us as a city killer or two, probably multiple decades away, probably hitting in places that don't matter, okay, which will allow us to practice doing things right. Now, in the course of learning how to do this, the easiest thing to do, there's lots of ways to do this, the easiest thing to do is smash stuff into it, little stuff so you don't break it up into pieces. You have to be careful with like nuclear bombs and stuff like that because you've got a rifle bullet coming towards you and you don't want to turn it into a shotgun shell. That's bad, okay? So it turns out that you can move asteroids around. You can get them from where they are into Earth. If you are willing to spend 10 tons of xenon fuel in a solar electric propulsion vehicle, you can retrieve a 500-ton asteroid into orbit. And NASA's actually working on this. And remember I was saying about how if you do this 14,000 times, you can build Kalpana 1 in low Earth orbit. Now, this is of course ridiculous because this mission that is probably cost between $1 billion and $2 billion, meaning the total cost would be $28 trillion. Except that the first one's the most expensive one, and the first one's already being funded now. If you were to do this mission 14,000 times, by after a couple hundred, you should be able to pretty much automate it, and the cost should come way, way down. So it's not quite as ridiculous as you might think it is. It's just ridiculous. The National Space Site that I'm part of has an official policy on planetary defense. We would like other organizations to join us, possibly wanting to modify it a bit. And the basic idea is it says, this is really important. This is existential. If we get hit by something big, and we certainly could, nothing else matters. Nothing else matters. We really should do this. And we should be willing to devote a large fraction of our space budget to it, but we don't have to. If we can devote 1% of the civil space budget worldwide, we can have a crackerjack program. We can do all kinds of detection. We can study deflection. We can do everything we can possibly want to do for 1%. And it's really kind of ridiculous if we don't do it. So as I said, to do that, the focus needs to be on detection for reasons we already talked about. And we need to look at long-term comets. This is, you talked to me after. And the remaining funds can be put into characterization and deflection. Okay. So what? I kind of dragged you through all this tourism and space, solar power, and planetary defense stuff. Does not even orbital settlement. Well, if this works, what we will get out of tourism and space solar power, if they take off, is we will get low launch costs because we will get volume and lots of it. Tourism, if it takes off, will give us life support, because they're gonna have to develop it in order to keep their customers happy and willing to pay those big bucks to go up there. Space solar power is going to teach us how to build very large structures, kilometer scale structures in space, and to be able to develop large amounts of power. Planetary defense will tell us where the materials are. It's a map of the solar system, say here's where all the good stuff is. You know? Go get it. So that's most of what we need. So instead of needing a truly titanic amount of government money, we'll only need a lot of government money in order to. So I'm sure you can read the conclusion. I just want to bring up one. I think we actually have a duty to do this, to build space settlements, in particular orbital space settlements. And what I mean by that is that we are the only ones that can do it. The dolphins can. They might be smarter than the whales may be smarter than us, but they can't build spacecraft. You know, the monkeys someday may be smarter than us, but they can't build spacecraft either. Only we can. Only we are spacefaring. Life depends on us for growth off of this planet. Life has been growing since the day it was created. And it's stuck on one thin film on the exterior of the third rock from the sun. In this vast universe, that may be the only life. And if it's the only life, we have a duty to preserve and expand it and grow it. Or there might be lots of life out there. And if there's lots of life out there, there's probably some life that is like us. And if they are like us, we had better find them before they find us. Thank you very much. I'd be happy to take questions. Yeah.
So you have companies like Planetary Resources that
Yeah.
are pulling in asteroids and using that as a way. Like, would a fourth, possibly a pillar of building these large-scale settlements be to take the planetary resource route and use that to fund the mission? Use that to be grounding materials anyway and pulling them to Earth.
Okay. Well, full disclosure, I have a fairly close association with Deep Space Industries. Okay. It is my opinion, and then the reason I am not a founder of Deep Space Industries, that there is the probability of making a profit off of anything but government contracts doing asteroid mining for quite some time is epsilon, which you learn about in your calculus classes. And actually quite a bit smaller than epsilon. The thing is, it's hard to do. Asteroid mining is hard to do. It's fun to do. And I encourage you to go out and do asteroid mining. You know, think about it, write papers and do calculations and design systems, but it's extremely difficult to do. It's extremely difficult to sell asteroid products on Earth because although things like platinum and so forth are very expensive, they are very cheap compared to bringing something from a heliocentric orbit onto the Earth. Okay? You might be able to make a little bit of money if NASA brings an asteroid into lunar orbit and then lets you add it, which is quite possible. You might actually make a little bit of money selling to collectors who will pay ridiculous amounts of money for very small meteorites. Okay? So selling on Earth in any kind of bulk is probably out for a very long time. So the markets you're really depending on to do actual asteroid mining is basically water to produce fuel to sell to spacecraft. And you got a horrendous chicken and egg problem. You have, the market today is zero, okay? And the big market is ComSats for station keeping, but they use hydrogen. They don't use hydrogen oxygen. And they are going to solar electric. And solar electric has a exit velocity 10 times that of chemical propulsion. And with the rocket equation, that's underneath the divisor sign in the exponent. Okay, so all you computer scientists know that you just get massacred again. You can't compete. And the total amount of mass you need for an electric propulsion vehicle to station keep or do transit is very small. So it's really difficult to be able to pay for all that thing. So, I mean, basically, if I would not start an asteroid mining company because I could not look an investor in the face and tell them anything but you will lose all of your money. Okay. That will not always be true. And one of the steps that we need to take in order to make it not true is what the government ought to do, which is find where all the resources are. So that's my opinion. It would be great if I was wrong. Okay. There was somebody back there that had a question? Yeah.
If you ignore the problem of getting the resources into space or out of asteroids into one area of space, what are our current capabilities in space construction?
The current state of the art in space construction is you take pre-built modules and launch them, and astronauts do EVAs and put them together. And obviously, it's very expensive for astronauts to do EVA. A person in a spacesuit is not nearly as capable as a person not in a spacesuit. So this is a tremendous opportunity for robotics. And there are actually, and there are near-term markets too, in doing things like repairing ComSats and adding additional station keeping. So this is a very undeveloped area. There are a lot of robots on the International Space Station, most of which are sitting around doing nothing almost all the time. So I think it would be interesting to do some proposals to use those robotics to start developing those kind of capabilities. The only money in it at the moment is going to be government contracts. But in case people don't know about it, there's a really tremendous opportunity to do work in space. There's an organization called CASIS. They were created by Congress with $40 million a year, and half of the American resources for the International Space Station. Half of the astronaut time, half of the up mass, half of the down mass, and access to any American facility on the station for free. For free, okay? And you can send an unsolicited proposal to CASIS. You know, they have solicitations. They say, we would like some proposal. You can send an unsolicited proposal to CASIS, and they would really like to do it if it's a good proposal. Okay, they will try to do it as a proposal. So particularly, you're working in these labs, is go to their website, poke around, and find out in the detail the amazing free resources that you can get out of this organization, and put it together with your professor and do some space robotics. There's a just wide open field. There's some great robots up there. Unfortunately, most of the robots are not American robots. So the best robot is a Canadian robot. So you got to, but you're not very far from Canada. You can make some friends up there. Yeah.
I was wondering if could one of the other paths or motivations be for any sort of settlement that's in space, or orbital space, could any sort of telescope work be expanded that, like interferometry being usable on a large area that would only be able to be found in a satellite?
Right. Yes, there are things like that, but it's not a large market.
Okay.
I mean, it's, you know, if it's very, very successful, you might get to do 1 or 2 a year, right? And that's great. I mean, we should definitely do it, but it's not going to fund. It's not going to require 10,000 launches a year. It's not going to. It's not going to drive your capabilities up by huge factors. Which is that's not doesn't mean you shouldn't do it. There's lots of other things like growing organs in space and doing bioresearch and crystallography and all kinds of things, but none of them, to my mind, have the volume, the mass of tourism in space solar power. Yeah.
I guess this kind of ties into an earlier question, but how possible would it be to just expand the ISS as one of the small steps to looking into orbital hotels or something similar, especially since we could land a Dragon onto the ISS itself? Yeah.
Well, I mean, the ISS is a space hotel. It is the first space hotel.
Commercial users, just expand the...
Well, it's a government facility, and the reason the Russians started the U.S. government can't do that politically. I mean, I can see Jon Stewart talking about this, right? And it doesn't look good. And I can see Rush Limbaugh and those guys just ripping it to shreds. The Americans can't do it. The Russians, of course, have done it, but the only reason it worked for the Russians, even at $20, $30, $40 million a pop, is that they have to fly, the Soyuz is used as a lifeboat on the International Space Station. And so you have to have enough lifeboats on at all times to take the crew home if something goes wrong. The Soyuz has an on-orbit lifespan of 6 months. So after 6 months, you have to change it out. It takes 2 guys to fly a new vehicle up there, and there are 3 seats. That's where that program came from. It also came from the demise of the Soviet Union, and all of a sudden the Russian space program, which is a fantastic space program, had no money. No money. But they had very cheap engineers. So $20 million went a long, long, long ways in those days. But these are very unique circumstances. Yes, you can make it a little bigger, and Bigelow is putting a module up in there. but you're not going to be able to, again, it's not something that's going to expand hugely. It's not something where you can generate thousands of launches a year and fly tens of thousands of people on it. It's just not big enough. Yeah.
So these, what you're talking about tonight, these are why we're going to go into space. But what's gonna like let us stay there? Why are we gonna stay there?
Oh, you mean,
So like asteroid mining, right? So
it's a means to an end.
it's like drilling for oil in the ocean, but no one builds a city around an oil rig.
Right.
People not build a city in Deepwater Horizon. So if resources and energy and towards that make us go out there, what's gonna keep us there?
Well, I think, in the long term, it's a real estate business, okay? Which means the price has to really come down. Because, people are willing to pay a few years' salary for a house. And maybe if you get to live in space, we'll add a few more. But if you just work out the numbers, we're not even in the ballpark. We have multiple order of magnitude to go. I mean, I think there are some groups of people, who would just like to live in space. That's what they want to do. I mean, when they had this Mars thing, where they're going to send people to Mars one way, and you couldn't even come back, they had 180,000 people sign up. Right? And it's nuts. You can go up there and hate it, and you're screwed because you can't come back, and you're probably going to be dead within a year. Nobody knows how to grow plants on Mars. If you can't grow plants on Mars, you will die. Okay, you can't figure it out jolly quickly. And there's precedent for this. Jamestown, the first successful British settlement in North America, they had a 90% per annum fatality rate. The Pilgrims did much better. They had a 50% per annum fatality rate. Okay? So this proposal, and they actually got 180,000 people to go to say they wanted to go on a suicide mission and pay for it. So there is a desire. There are people that will do it. The 7 billion people on the planet, there are some people who just want to go. Right? And a lot of them will wash up. They'll get up there and they'll hate it and they'll come back. But some will stay. Right? My prediction, the maid on the hotel, when you have space hotels, you're going to have maids and repairmans and concierges and managers and stuff like that. They're going to be living up there. My prediction is some of them are going to want to stay for whatever reason, and there's going to be a bunch of regulations that will not allow them to stay, and they will evade them somehow. Right? And those will be the first permanent residents in space. Yeah?
So on the one side, we talked about how the Falcon right now is about $6,500 per kilogram.
That's for an actual flight that actually occurred.
What do you think is going to be some of our avenues of bringing down that price, whether it be like making it lighter, more efficient engines? What do you think is going to be our current work?
Watch Elon Musk with wonder. Literally, I think that's true. He is a very smart guy with a lot of money and has been fantastically successful, although he came that close to getting hosed in the early part of the mission. They're looking at reusability. They're flying experiments. Reusability theoretically should drop costs. It did not with the shuttle. Okay, they have their production system. They're constantly improving. They're going to 40 cores later this year. They should be producing 40 cores a year. Each of those has 9 engines. That's 360 rockets a year. That is a huge rate compared to anything previously. They're doing all the right things. It's really a great thing, and I think that they probably are a lot better at making rockets cheaper than I am. And so right now it's SpaceX's ballgame. They are the best thing in town, and everybody's Ariane is dropping their prices, right? Because they have to in order to compete. Otherwise, all the geo traffic will go to Elon Musk. I mean, long term, you have things like you can have lasers that melt ice on the back of your vehicle that send it up. There's a scheme, a friend of mine, Keith Henson, that you pop up with the suborbital vehicle, the big block of ice in the back, and then you have an enormous laser in geosynchronous orbit that blasts the ice, and you can get very high ISP with that, extremely high launch velocities. And he's done a bunch of calculations, and it's this enormous system that costs, he got all excited a few years ago because he got the price from 150 billion down to 90 billion. It's really hard to raise that kind of money. But there's a whole bunch of people doing crackpot schemes, and maybe one of them will work. okay? You can have electromagnetic assist on the launch. You can just have economies of scale. You know, if you could just fly 500 or 600 times a year, that would help a lot. You can build new spaceports. You can launch from Texas and drop off your first stage at Kennedy. There's a whole bunch of, and like I said, this is a golden era of launch development. Right now, right here, and you guys are going to have the opportunity to go work for these companies in a couple of years. Yeah.
Do you foresee in the future eventually the connection of space elevator to even greater help with the launch costs if there are no launches?
I mean, space elevator is really cool. I once started a whole program at NASA because I thought that nanotechnology might give us space elevators. Right? I got a little award for it, shortly after they canceled the program. Just saying. And so it's really hard to do. It's really worth working on, okay? But there's a really severe problem that people have not looked at. I ran into a guy once who did his master's thesis on a lunar elevator. And he looked at the micrometeor collisions. It turns out you're going to have a lot of them. Because even though it's very thin, it's very long. The total area is quite large. And so you're going to be having to constantly repair this thing. And that might be a killer. I haven't sat down and really worked out the details, because it's hard. But it's worth looking into the micrometeor flux and how often you're going to get hit, and whether you're going to be able to constantly do those repairs and make the whole thing work. So if you want to do a project in the area, which is really, really interesting, that's what I would do. Figure out if the micrometer makes it impossible. Somebody had a question. Yes.
So speaking of crackpot schemes, Ronald Reagan was dead serious about planetary defense in the meeting of like bombing Russia from space.
Yeah.
Is that in the water? Is that still on the table?
I'm sorry, what?
Do people still talk about that as an option, or after Ronald Reagan left, are we done?
Well, no, I mean, no, we're spending tens of billions, either singles or tens of billions of dollars a year on missile defense, right now. But now, I mean, everybody's given up on stopping a big Russian attack. You know, we know we can't do that. Okay, it's all air defenses are attrition defenses, right? There's no brick wall, and there's just, you know, you can overwhelm any defense by just simply firing off more missiles. So right now what they do is they're justifying 5 or 10 or 15 billion or whatever it is per year on the theory that they're going to be able to stop a North Korean attack using a vehicle they don't have and a bomb they haven't built. But these things do take a while, and things are not going well. They're having tests where they're missing. It's a kinetic hit system, and so you actually have to hit the ballistic missile coming towards you. This is really, really, really hard to do, and they're not doing it very well. And there's a couple of facilities, and they have some rockets and stuff like that. And I would be shocked if the Koreans actually attacked. I would be shocked if they were able to stop one of them. And if the Koreans were smart enough to fire 4 or 5 or 6 off at once, there's not a prayer, not even a remotest prayer of stopping all of them. You might get 1 or 2 if you're really lucky. So Star Wars lives, but it's, you know, in the real world, it's trying to be operational, and things are not going well. Any other? Yeah.
Blue sky for a second. If this goes on.
Well, the rest of this wasn't blue sky, so it was like. Yeah, go ahead.
If everything goes well.
Yeah.
I'm mostly right. From today.
Right.
How soon could we get to Kalpana 1?
Well, if we were to start today with essentially infinite money, some small number of decades, right? I think though, it's actually, if I was told, okay, build Kalpana 1, I would do tourism and space solar power first, and planetary defense. I would do those first because it develops so much of the technology you need, and you're gonna come up with a whole different solution once you have that stuff. Plus, you can make a little revenue in the process. But I mean, the absolute minimum is some small number of decades.
Thank you.
Yeah.
What kind of animals would we bring into space if, like, we had to do that? Like worms or anything?
Well, you certainly want worms. If you want good tasting food, you need soil, and so you need worms. I think if it's Americans, they're going to want dogs and cats. Okay. Other cultures have other pets. I think you want like goats and chickens and maybe rabbits in order to consume the stalks and you know, the stuff, the non-edible parts of plants. You know, rather than trying to compost them directly, I would feed them to chickens, goats, and rabbits, and then take the feces and then you know, convert that back to so those are the things I would expect. There also may be some stuff that you didn't really want. You know, particularly at the microbial level, there might be a lot of stuff you don't want, and you know, insects that make their way onto the station that you didn't want. You're going to need you need stuff like ants in order to clean up. And so getting the insect balance right is not going to be easy. That could be quite a problem.
Build the ISS, we basically launched parks that have been built in the ground.
Yeah.
Now, to build a settlement like that, do you think we would actually send out machines and material that would make those parts come alive in space, or?
Yeah. I think you can't launch something 500 meters across. You just can't. You know, so you're going to have to send out pieces or get materials, you know, from the moon or the asteroids and remanufacture them in order to build this. So it's, you know, there's a 3D printer up in space now, or that you know you can get access to. But we're just at the very, very beginning of that. There's people that have schemes for different sort of scaffolding and ways to do it. And then some people imagine printing the whole thing, or you blow up a gigantic balloon and then you deposit, you know, do vapor deposition on it because the vacuum is easy to come by. There's lots of schemes, but you're certainly not going to be able to launch the thing whole from Earth. No way. You probably certainly get from Earth, you know, your electronics, small specialty pieces that you can't make in orbit very well, things like that. But you'd really like to make as much of it out of lunar asteroid materials as you can, which will finally give a good market for the asteroid miners and the lunar miners. And then they'll have a market, you know, and you can make some money. Anything else? Well, thanks again. Really appreciate it.
Give you something from SEDS. So thank you so much for coming. It was great to meet you, great to have you present. So I will give you a nice green laser pointer to
perfect. It was complete with batteries and everything. Perfect. I actually need something like this. So I can take it. Thanks.
Yeah, thanks everyone for coming. And I think there's a little bit of food left, and you know, do some homework. Just trying to stay alive. But again, thanks for coming. We appreciate you coming out. Oh yeah, so here's nice tickets. See me if you want to or buy some. Or assuming medical technology increases, for like what, 150,